Floating offshore wind farms use cutting-edge technology to generate clean, zero-carbon energy and are expected to become a game-changer in the global energy transition. They are located in deep waters and further offshore to take full advantage of stronger and more consistent winds to produce affordable and reliable energy, revitalizing coastal communities and generating future-proof jobs. The development of a floating offshore wind farm involves a thorough analysis to ensure acceptability by the local stakeholders and compatibility with the other users of the sea. From the onset, it is important to analyze the visual impact of floating offshore wind farms on the coastal communities. For that, Plain Concepts was challenged to create a realistic and scientifically rigorous visual representation of a floating offshore wind project. To deliver this, we have worked with Evergene, Plain Concepts' own graphic engine for business and industry. This video explains the thorough process followed to create a 3D virtual simulation of a floating offshore wind farm. First things first, we need panoramic photography. Once we have the panoramic shots, we select 2 representative points of each spot. In parallel, we define the horizon line. We'll use it as a reference to place the turbines. We then choose the 2 closest points to the exact floating offshore site to minimize precision errors. It is important to highlight that these 2 points should also be iconic coastal viewpoints. The GPS coordinates of our 2 iconic points, plus the GPS coordinates of the exact position where panoramic photos were taken, yield interesting information through the use of trigonometry. We get the distance at which the floating turbine will be placed. We obtain the angle from which the floating turbine will be seen. These new data points will then allow us to position the coordinates of a new point on the image. At this stage of the process, we have been able to translate angles into image pixels. Now it is a matter of iteration. We will repeat the same process for each turbine, so we will then have the exact layout of the entire floating offshore wind farm on the image. Next step, calculating the size of the turbines. To get the size in pixels on the image, we need to first get their angular size. The angular size shows the size in degrees of the object and is calculated using 2 key data points: distance to the turbine. Remember, we got this number in the previous step. Size of the turbine. We will get this information by using a CAD model of the type of turbine to be used in the project. As floating technology allows us to go much further offshore and the Earth is not flat, turbines can be hidden behind the horizon. We need to calculate exactly to what extent the turbines will be hidden, taking into account where the photo was taken. Factoring in the height of the sea level and the distance to the turbine, we obtain critical information. Horizon distance, distance at which turbines will be completely hidden behind the horizon and thus invisible. Hidden height, the exact segment of the turbine which is hidden behind the horizon. We now know the exact position of the turbines, their distance and the extent to which they are hidden behind the horizon. That is to say, their hidden height. We can therefore determine by how many pixels the turbines are hidden. Last step, we should understand the predominant direction in which the turbine blades are oriented. The nacelle of a wind turbine rotates searching for the best wind resource. For this, we use the wind rows for each site. The blade's orientation will change according to the wind direction, and thus, we will have a different view of the turbines from where we took the original panoramic photos. Often, the predominant wind direction is parallel to the coast, and as a result, we would observe a profile of a turbine rather than have it face the coastline. And that's all. This is a quick guide to the methodology used when developing realistic 3D visual simulations of a floating offshore wind farm.